Hello, I'm talking about the VISCACHA survey today, and this is about star clusters in the Magellanic Clouds, in the outer parts of the Magellanic Clouds, and why. So before starting, I would like to invite you for an experience. So go out tonight and look for the Magellanic Clouds out of your neighborhood. They're beautiful, aren't they? Well, I think that maybe if you're in Cordoba or in large cities, you have light pollution that's preventing you to see the beauty of the Magellanic Clouds. So this is something really bad for astronomy, for human beings and animals as well. So be aware of that and help fight against this and find intelligent solutions for that. Even if you're in a dark sky area, we have a new concept for light pollution now that's on space, for example, the satellite constellation. So this is a big issue. We have big investments in telescopes, so please join any efforts to find solutions for that. Okay, if you were in a very dark sky, you could see that, at least part of that, depending on where you are on Earth, and you can spot the Magellanic Clouds beautifully on sky. If you could add another layer and see gas, so that's what this survey did in 1974. Basically, the map of gas of the entire sky revealed the Magellanic Stream. Magellanic Streams is this 200 degrees wide structure around the Magellanic Clouds that's actually revealing that the Magellanic Clouds are orbiting the Milky Way, and this Magellanic Stream is the trailing that's left behind the orbit. And that raised a lot of questions, of course. So what's causing this? Could be room pressure because of the hot corona of the Milky Way pushing out the gas from the SMC, for example, but could also be a tidal stripping effect. If it were tidal stripping, then it should be an opposite, two opposite structures, right? But the opposite, the leading part, would be crossing the Milky Way, which is really hard to observe. So with a new technique and more detailed analysis and observations, there was a confirmation, a Nature paper also about the leading arm. So apparently tidal stripping is taking a huge portion of the effect that caused the Magellanic Stream. Of course, room pressure is also present, but the tidal stripping is the most important thing. Okay, so Msun and collaborators were right in 74, and there was some structures there that they could spot but could not confirm. But this also raises a lot of questions now, right? So if it comes from tidal stripping, so the tides come from orbits and interactions between galaxies, that could be only LMC and SMC as a pair, causing all of it, and could be an alternative using the Milky Way potential also. And if this pair is orbiting the Milky Way, so the three galaxies together are necessary to form these structures. So what is this? And another point that's very interesting is that Milky Way type galaxies with this mass usually do not have satellites as massive as the Magellanic Clouds. So this is big. For example, in the millennial simulations, they found less than 10% of such cases. So why is that the case, and why we are so special in this case? So there's two discussions of the scenarios that explains why the Magellanic Clouds are surrounding the Milky Way. One of them is the classical, and I put that as a second point here, that says that the Milky Way has the LMC and SMC as their satellites for a long time, but they were separate and they just became a pair about 5-6 billion years ago, and they're orbiting. So everything can be explained with this framework, right? But recent proper motions and updated mass for the LMC and Milky Way actually proposed a different model to explain that, and a different framework to understand the past history of the Magellanic Clouds, saying that the LMC and SMC has always been a pair, or at least for a long time, and they just arrived in the vicinity of the Milky Way. So they are just in the first infall scenario. And this scenario has been collecting different evidence from everywhere. And there was a paper on Nature last week, so super recent, with another independent evidence showing that a prediction from the models was confirmed with observations of concentrations of stars in the really outer halo of the Milky Way, which is only explained by scenario where the LMC is in the first infall. Okay, so apparently we are moving towards this scenario framework that the LMC and SMC are a pair coming to the Milky Way right now. Okay, and this, I mean, thinking about lambda CDM models and satellite galaxies. Now that we have a lot of surveys, we are collecting a lot of data about satellite galaxies, dwarf galaxies, all kinds of them. And they seem to be organized, some sort of organization there in the sky. And for the Milky Way, for the LMC, sorry, there is a prediction from models, for example, from the Illustris simulations, okay? So that apparently the LMC could have brought about 7 dwarf galaxies. Apparently, they are ultra-faint dwarf galaxies, not classical ones. And there are a couple of them that are on the way of confirmation. So apparently, they are related with the LMC. So the LMC brought with it its own satellite system, right? So all the Magellanic Stream and leading arm, all this Magellanic system is very complex. And also combining this with the LMC wake that was confirmed last week, we can say that the Milky Way halo is not on equilibrium. So there is a lot happening there, okay? And again, instead of finding like final answers or just raising more and more questions, right? And the questions here now are about stellar populations. And here I'm coming to my point on the talk. So the stellar populations on the Magellanic Clouds are affected because you're talking about gravity, you're talking about tides, and these moves stars, okay? So what is the effect on stellar populations that you can detect that could in turn maybe put some constraints on the details of these models and further constrain or tighten the constraints for these models, for example, for the first infall scenario. So the tidal stripping, okay, so stars should move also along with the gas, or maybe even in different directions and different stripes and streams and bridges and so on. So where are the signatures? So you have to find and look for them. Need surveys, stellar surveys, okay, stellar observations, photometric surveys. And the collisions would also change the structures of the galaxies themselves, okay? So for example, for the LMC, apparently with a direct shock of the SMC with the LMC formed a ring around the LMC. And the SMC seems to have a lot of tidal tails on the bridge that connects with the LMC. So there is a lot happening on the structure there that could tell us about the past history. And also about the wet collisions, right? SMC is gas rich. So with a collision could trigger a lot of star formation and star cluster formation. So you would be able to see that if you can measure the ages of these stars and star clusters, okay? Also, when you have this, I mean, if you consider the LMC and SMC as a pair, they are not in a constant distance between themselves. So they are oscillating, and this oscillation also changes the base potential well of the star cluster systems. And actually this could also help or boost the dissolution of star clusters. So there are many things that we can study with that. And here I put a timeline of science conference, the big science conference on Magellanic Clouds. And you can realize that there is like a more frequent occurrence now, that Magellanic Clouds are becoming more and more interesting because of the data, basically, right? And I put some milestones here of the Magellanic Streams cover and the leading arm confirmation and the first passage scenario that was proposed in 2007, okay? And after that, there were many surveys on photometry for the stellar populations, right? And they are accumulated here, kind of a coincidence. It's not by chance that I blame basically the telescopes that are dedicated to surveys. Okay, so the advent of the large telescopes of the 8-10 meter class left space for the smaller telescopes, the class of 2 to 4 meters, to be dedicated to surveys. So we had a lot of things to do on the southern hemisphere here. And the VISCACHA survey comes a bit shifted from that, because the VISCACHA is a further step, and I'll tell you why. So here, a couple of examples that these all sky surveys, or at least large area sky surveys around the Magellanic Clouds, are covering the interesting parts, right? So if you think about the dark energy survey on the right, it's not dedicated to the Magellanic Clouds, but it's covering the Magellanic Stream. So we have a lot of information there. The VMC is in infrared and with variability. So you have area leaders and cepheids that can derive many parameters there on the bridge and the stellar populations. And SMASH survey is really deep photometry to try to find the stellar counterpart of the leading arm, for example. So why we are interested on star clusters? Why they are so interesting if you have like stellar population? So why they are important? They are objects that provide a lot of information in a self-consistent way, and that could provide constraints on the general population of the stellar population of the SMC, LMC, and bridge. Okay, and the thing is that they are everywhere. So they are in the bridge, they are in the counter bridge, they are around the bar of the central parts of the galaxies, and they have different ages, they have different chemical compositions, they have different movements like velocities or proper motions. So they are spread out, they bring with them a lot of information. So it's just a matter of us to go there and put this information in an organized way so you can try to interpret in a general sense. Okay, so in the left here, show the radial density profile and surface brightness profile of a cluster. So you can derive the structural parameters like the tidal radius, for example. On the right, you see the color magnitude diagram, so from where you can derive in a self-consistent way age, metallicity, distance, and extinction or reddening. And also on the bottom, you see the luminosity function that can be converted in mass function using the CMD parameters, right? So at the end of the day, we end up with a 3D map of the SMC LMC bridge, pinpointing a lot of information like age, for example. So you could call this like a fourth dimension, right? So you have time. So you have the spatial 3D distribution of these clusters with the time information and the chemical information, if you want to call it a fifth dimension, and all the other parameters that you can use in a smart way. Right. But there are lots of photometric surveys, so why not go to them, public surveys, and trigger the data from there and study star clusters? Well, it's not that easy because the Magellanic Clouds are not so close. They are close enough so we can resolve the stars, but not that close so we can resolve easily the star cluster stars in their cores. Okay, so I put some examples here on the bottom. See famous or the most important stellar surveys. Okay, the class of telescopes of 2 meters that produce shallower photometry and the 4-meter telescopes that produce the deeper photometry. But all of them have one thing in common. They are limited by the atmospheric turbulence. The seeing limit is limited by the atmosphere, right? So you cannot do much more better than that. Okay, but maybe hoping that the sky is a very good seeing at that particular night, but to do like a large scale survey is really hard. So you could go to space. Gaia, for example, produces a lot of data, but is a shallow photometer, so does not serve for old star clusters, for example. And Hubble is useful and perfect, but only for a couple of handful of clusters previously selected, not for a large survey or so. So VISCACHA survey comes to the rescue with adaptive optics. So that's the best compromise to do what we need to do with star clusters, okay? So you do use the same 4-meter telescope, class telescope, the SOAR telescope, but equipped with adaptive optics. So we can correct at least the ground layer atmospheric turbulence. And with this, we can reach a better photometric spatial resolution. Okay, so with this is enough for us to observe star clusters like this. So on the right, I show you a beautiful image from the VISCACHA in color. So that's the best performance you can have with SAMI instrument and SOAR. So reaching 0.4, 0.35 at best arc seconds in I band. And on the left, I show an animation here comparing the core of this cluster between VISCACHA and SMASH survey. So SMASH is great for field stars, but for the core of the cluster is not useful. And here I do an experiment here showing the CMDs, the color magnitude diagrams for these different regions, the different rings around the cluster. Comparing the SMASH and the VISCACHA photometry, you can realize that the SMASH and VISCACHA are comparable in the field. So they're really deep, very good photometric errors, and everything resolved. So they're comparable. But as you go deep into the cluster, the VISCACHA can recover the stars down to the faintest magnitudes without a problem and produce clean CMD for the star clusters from which you can derive all the parameters. And SMASH fails to do that because it's limited by the atmospheric turbulence. So what we are doing with the VISCACHA team, so we have 30 members, roughly around 5 countries, including Argentina. And here, an infographic here showing this current status of the VISCACHA survey, where 70% of our goal, that is half of the outer clusters in the LMC-SMCM bridge, which we believe that will construct a map, representative map of the outskirts of these galaxies where the tides are most important and can trace better the past interactions between these galaxies, right? We used already about 500 hours of telescope time to observe almost 200 clusters so far. I highlight some topics here, but I'll put here some of the answers to these big questions that I mentioned before concerning stellar populations. That we already made some contributions within the VISCACHA collaboration, okay? So before the VISCACHA data, I did some collaboration, some contribution here that was during my PhD thesis as a final paper. I proposed that the SMC outer regions, that's the map of star clusters from the BICA catalog. So the outer regions of the SMC in particular should be or must be analyzed in different parts, in different regions, as it seems that each region represents a different history of a tidal interaction, of something, collision or something, don't know why. And that's the case of study. So that's the framework that we established there, and from where we started studying and scrutinizing the SMC. Okay, so apparently the wing bridge, so the SMC wing and the bridge that actually coincides with the gas bridge. So that would be the young bridge. The southern bridge would be the old bridge that's earlier. Okay, so this is well known before, but the other parts are a bit fuzzy from observations, a bit here, a bit there, some models predicting something, but it's nothing clear yet. So starting in 2016, I analyzed the west halo that apparently was forgotten in any studies before that as a structure itself. And I seemed to realize that this west halo structure seemed to resemble the main body. So apparently it was part of the main body in the past and moved away. And 2 years later, proper motions, that was the way to confirm that, from Hubble, Gaia, and VMC together, and two independent studies confirmed that there was proper motions in this direction, showing that this region is moving away from the west here, from the main body. So apparently this seems to be like a tidal stripped region or something of the sort. So here, as I mentioned before, there is this young main sequence, Magellanic bridge, and earlier bridge. So apparently the young bridge is in the same region as the gas bridge, meaning that when the gaseous bridge was formed, it brought some star formation. So all the stars there should trace the age of the gaseous bridge. That's basically that. And the other is a older bridge traced by Areliris. That's an old population tracer, right, from 10 billion years or more. So there is these two structures there that, of course, have two different histories, but they are apparently in the same region. So the thing is that now we detect the third branch of the Magellanic Bridge. So earlier this year, we studied some star clusters in this region here, north to the classical Magellanic Bridge, and we find out that using now some contribution from Argentina here, because we had the GMOS and Gemini, some data on radial velocities, and plus proper motions from Gaia and distance from the VISCACHA survey and the positions from the BICA catalog. So we have the full phase space vector for these clusters, and we could recognize that there was a bridge structure there as well, pointing to the LMC. And we found for the first time the first cluster that is the candidate to be the first point of the structure that should be the tidal counterpart of the Magellanic Bridge. So the opposite direction there. This cluster is moving away from the LMC. Okay. So a third case here is the gradients, the radial gradients of metallicity age. So Celeste Parisi, who you may know very well, detected this V shape or this inverted gradient beyond 4 degrees from the SMC center. So when she derived some metallicities from spectroscopy for a couple of clusters from the SMC, she realized that beyond that there's something happening there at 4 degrees from the center of the SMC. With a compilation from the literature, BICA catalog, we made some compilation of all ages and metallicities we could found in the literature. Of course, this is heterogeneous, not as homogeneous as Celeste Parisi's work, but we can already see some trends there and kinds of resembles what Celeste found. There's something happening there at 4 degrees. So more recent, there was a derivation of determination of the tidal radius of the SMC, which, surprise, surprise, it's about 4 degrees. Okay, so from the SMC center. And we know from extragalactic studies and observations and simulations that inverted metallicity gradients usually are related to some collisions or galaxy-galaxy interactions. So if beyond 4 degrees, these clusters are not within the tidal radius of the SMC, it's very likely that these structures that are outside, for example, in the bridge, were formed due to an interaction between the LMC and SMC. The bridge, we already know that, but let's see what happens with the other regions. So that's for the future now. Cluster dissolution. So this is another topic that I mentioned there in the beginning for the big questions in stellar population. So here, one point is that there is a discussion, an open discussion there in the literature about how a star cluster should dissolve based on internal effects only, like evaporation, for example, and two-body relaxation. Okay, one says that it depends on the mass of the cluster, other says that it doesn't, but essentially they are linked to the available data that's incomplete. Okay, so there are missing data there that's incomplete for low mass clusters that are really old. And the VISCACHA survey should fill this gap there and provide some constraints in this direction. In fact, on our paper 1, we found that AM3 is actually losing low mass stars. So it has a low mass, it's really old, and it's losing its low mass and in the mass function. So it is actually being dissolved right now. So we found the case there. So we are moving there to get more and more data points in this plot. And another way of understanding cluster dissolution and putting some constraints also in the interactions between SMC and LMC, it's a bit more complex, but can explain very simple. It's related to the Roche volume, the Jacobi radius of star clusters orbiting a galaxy. So let's say that there is a cluster orbiting the LMC. Okay, so it has its Jacobi radius at zero velocity, right? Defined by the zero velocity. And the tidal radius, if the cluster is relaxed. So the tidal radius, all the stars until it reaches a zero density should be filling this Jacobi radius, and everything is in equilibrium, everything's perfect. What happens if the cluster has, elliptical orbit and has apocenter, for example? So when it's really close to the LMC, then what happens is that the Jacobi radius will shrink, okay? Meaning that the stars that are really close to the tidal radius will be outside the Jacobi radius and more susceptible to be wiped away, okay, by the gravity or the orbits and tides and so on. And then when the cluster moves, if let's consider that the cluster wipes all the outskirts, and then this core will move away and find the apocenter, okay, when it's really far away from the LMC. And in this case, the Jacobi radius will be large. So if it's large, then the cluster has some time to relax, right? Dynamically relax and puff and fill in the Roche volume, okay? So this is the dynamics. So the cluster can be boosted, its dissolution can be boosted by some external variation of the potential well of the host galaxy. So what happens if you have a system of star clusters surrounding the SMC, for example, and we know that the SMC is closing and going away from the LMC. So the base potential well of the galaxy is changing. So it's not even the star clusters that's changing the orbits of the distance to the galaxy, but the galaxies themselves are interacting. So the system is much more complex here. But you see the point now that the star clusters dissolution is not based only on the internal effects of two-body relaxation, but also influenced by these external forces and very variable potential of the galaxy. Okay, so here just a number to say that the Jacobi radius changed with the distance from the center of the potential well of the host galaxy, right? So what we are looking for here is a candidate cluster that just lost the outskirts and is moving away with the Jacobi radius increasing again and didn't have time to relax again to fill in the Roche volume. In other words, would be underfilling its Roche volume, would be having a Jacobi radius that's much larger than its tidal radius. That would mean that this cluster just passed through some stress there in its structure and especially in the outskirts. For example, AM3 could be such a case. So we were looking for that in our sample for the first 2 years of observations. We did find nothing. So we found only the overfilling clusters and some other border lines there, but I mean, nothing really strikingly evident that you have such a case. So we keep looking for these clusters. Okay, so just to wrap up here and put some ideas for the future. So what is next? So we are already observing spectroscopy. So to combine with the photometry, as I mentioned before, to have like a complete phase space of at least selected clusters, not for the entire sample. And this is in collaboration between Chile, Brazil, and Argentina. And the idea is to keep observing more and more to complete all possible candidates. For some selected clusters, you can observe with Muse to have a complete statistics and structure and the internal dynamics and so on. Synergy with other spectroscopic surveys. So now the next step will be spectroscopy, as you say. And maybe plan a VISCACHA 2.0 there for the inner parts of the SMC and NMC, who knows? My take-home message, VISCACHA survey complements the large photometric surveys, right? So it provides deeper photometry and spatially resolved for star clusters that is perfect for the study of such objects. And the trick here is the adaptive optics. The SMC outer populations, cluster populations, must be studied into regions, okay, as I split it before. The Magellanic Bridge has a third branch on the north. So that was the recent discovery. And the inverted age metallicity gradient may be related to some interactions between the LMC and SMC. So we should take a deep view of this framework also in all regions of the LMC and SMC. Okay? And the cluster dissolution, we already found one case at least losing low mass stars, but still we didn't find any clusters underfilling their Roche lobe. Well, that will be all for today. Thank you for your time. I'll be happy to take questions to send by my mail, for example.